So thank you for the kind introduction, and now we move from the inorganic chemistry to more to the biological part, and I'm very thankful to the committee to give us the opportunity to present some progress we made in developing a potential reference measurement procedure for ferritin in human samples. This work is actually included in a EuroMed project where we deal with, biomarkers for Alzheimer's disease. And it's located here in the work package 3, where we want to develop reference measurement procedures for metalloproteins. So Alzheimer's disease, as you very well know, is the most common form of dementias, and about 10.5 million patients have dementia in the European Union at the moment, and the number is predicted to double in the next 20 years, so it's a very pressing issue here and a health issue. And the metal homeostasis actually is thought to be involved in the development of the disease, and especially iron, copper, and zinc, and also aluminum. So that was the reason why we included ferritin as the iron storage protein into this project, which is quite a challenging one because it's a very large protein. It consists of 24 subunits, so there's a lot of things that can go on biologically in this protein. It contains of two types of subunits, the so-called light chain and the heavy chain. And even this ratio can change and vary between different biological species, between different tissue types. So if you have serum or you have a liver tissue, and even that adds to the complexity of the model. This protein is a molecule that forms roughly a spherical shell of 12 nanometer diameter. So you have to think of it like the shell only, and then in this shell there is included iron as a mineral actually. So it can have up to 40,000 atoms of iron included in here, but this is very hard to have a defined number of metal in here. So the intention here was to use isotope dilution. We heard a lot of isotope ratio measurements already, so I don't want to go into detail here. But the principle is you have your sample with a natural distribution of the isotopic ratios. Then you need a reference if you want to do double isotope dilution, and you need a spike material which has an enriched isotope. In our case for iron it was 57. In case of other isotopes, other elements, you need other isotopes. And then you produce blends of the sample and the spike and the reference and the spike. And if you measure them, you can in the end calculate the amount of analyte you have in your samples. That's quite more or less straightforward. If you have inorganic samples, you just can add your element. In our case, we have the problem that spike and analyte have to be in the same chemical form. Otherwise, you have the problem that they separate during sample preparation, they behave completely different, and in the end, you have nothing gained from using IDMS. So we need spike material. If you have a look at the ferritin, there are different approaches you can take. You can take the iron. The advantage is you can introduce your iron quite easily into the protein. The problem is to get a defined amount into it. If you do IDMS, you need the defined amount. Another approach we are looking into in the project is using the sulfur content of the amino acid backbone. The problem here is that one of the amino acids is an initial methionine. And in biology or in living systems, that's often removed. And it has to be removed in your spike material. I will come to that later as well. And there is another approach using specific peptides enriched in CS13 or N15 and do quantification via the specific peptides. So first of all, here are the different subunits of the ferritin chain. You have the light chain. I don't want to go into detail in this structure here. It's just in the light chain, the initial methionine is removed completely. We haven't seen them anyway. So you can say the light chain contains 5 sulfur from methionine and cysteine. That's a different story with the heavy chain. We could see both the chain with and without the methionine from human samples. So you have a varying number of sulfur here. It's 5 to 6. So first of all, I want to show you the approach using iron. You start with the upper ferritin, then you have to introduce the iron. Oh, that should be faster. Into the protein. There are different ways published in the literature. You can use a biosynthesis from bacteria or plants. The advantage is you get a very high iron loading, but it's quite tedious, and you have a lot of other proteins from the systems, so you have to clean up quite thoroughly. There is another inorganic method to introduce it using more salt, but as you can see with a sulfate, you introduce sulfur, and if you want to do both, you have a lot of sulfur load in your spike material that you don't want to have. So our colleagues at the University of Vienna, who are involved in this project, developed a new approach for the spike synthesis. So they used apoferritin in ammonium acetate buffer and introduced the iron directly using a solution in HCl. And then you have to remove your iron chloride by a centrifugal ultrafiltration, and you have your spike material. It's quite fast and easy, and you don't introduce any additional sulfur. So the measurement was then done using a size exclusion chromatography coupled to an inductively coupled plasma mass spectrometry, so ICPMS in this case. That's usually not used in biological systems, but we introduced a new way of looking at the proteins. The advantage is you have only 5 microliters of sample that you need. You can separate the individuals on the size exclusion, which you have to do because in the ICP you see only iron, so you can't say where it comes from. You can detect iron down to the 5 nanogram per gram level, so ICP is quite sensitive here. And you can also use iron and sulfur to quantify it and calculate the ratio of iron and sulfur in the protein. So that's what it looks like. If you have the apoferritin, you can see, I don't know do you have a laser pointer somewhere? Or maybe I can use them. Okay, thank you. So you see here quite large peak, that's the ferritin, but you can also see another sulfur peak here. I will come to that later. That can cause some problem, and you can see here it's only a very small amount of iron here, so it's really apoferritin. And then you load the 57 iron into it, and you get a clear peak here, where the sulfur peak for the iron was before. So this is what we got from the characterization. We have a total iron content of 3.27 microgram per gram, and the total sulfur content of 0.7 microgram per gram. So you have an isotopic, you have a ratio of iron to sulfur of 4.6%. And the enrichment of the iron in the ferritin was quite good, so 95%. That's good for a spike to be used. So you can see here quite clearly the difference between the natural iron and the iron we have introduced in your ferritin. The other approach, as I said, was using the sulfur. That's what we tried to do at PTB. We were not able to produce it ourselves, so we bought it from Trenzyme. They used a recombinant protein system with E. coli, where they produced the ferritin in an S34 enriched culture. Then you have to do cell lysis and heat, and they used heat denaturation and methanol precipitation because thankfully ferritin is a very stable protein, so you can do a lot with it. Then it had to be isolated using ion exchange chromatography and cleaned up with exclusion. And we got it in the end using in buffer and in a frozen form. And that caused some problems we did not expect. You recognize that peak again, maybe? That actually comes from oligomers, because ferritin unfortunately tends to oligomerize when you freeze it, and it tends to expand over time. So here, this is the peak for the ferritin we want to have, and here we have the peaks. No, it's not coming. I'm sorry. Here you have the peaks for the oligomers. So the challenge was now to remove the oligomers before we do IDMS, because otherwise we don't know exactly what we have in our spike. And I found in the literature a method they used guanidinium chloride at very high concentration with 2 molar. But unfortunately, it was not able to remove the oligomers completely. And then I recognized I did sample preparation, included also heat denaturation of the proteins in the serum. And I recognized after that the oligomers are gone. So why not use it to clean up our spike directly with it? And you can see the peak is a lot smaller here. Unfortunately, in both cases, we lose about 30% of our ferritin. So, but okay, we have to live with that. After that, we wanted to make sure that we actually have ferritin. It can happen a lot because you remember it's 24 subunits, and the E. coli produces the subunits, and then we have to make sure that we get the whole protein, we really get the chains we expect to have. And thankfully, our colleagues from the organic group, Andre Henrion, did some measurements for us. And we could see that we find both the light chain and the heavy chain with a quite good recovery. If you look into the specific peptides here that were used for the identification, you can see a clear match. I don't know if it's too small, and a very good precision here. So we have a deviation of the expected mass of 0.61 ppm, so that's quite good. And also the fragmentation, it's not coming. It's not working anymore.
To resume.
So it seems that one slide showing the coverage doesn't work, so we just skip it and go to the next one. As I told you, as we were sure now that we have the spike we intend to have, so the next step was to mix the natural ferritin and the spike material and to see if it can get a good 1-to-1 ratio, which we need for the isotope dilution, and if they behave more or less the same way. So I had ferritin and buffer, I added my spike material, did the whole sample preparation, separation with the column, detection via the sulfur, and I was quite happy. I got an isotope ratio, okay, it can be improved, but it's close to 1. So we thought, great, we go forward now and do the same with the serum. In serum, the concentration, the expected concentration is very low. So my first idea was a first step, just add the natural ferritin, like we did here with the buffer, and add the spike. And then something very unexpected happened. You can see here the ferritin peak expected is very small. It should be larger. And if you have a closer look at this part, you can see that the 34 peak is very small. So I started calculating, and I found that neither the natural ferritin nor the spike material is really recovered. And I'm not sure where I actually lose it in the sample preparation, because it didn't happen without the serum, so it seems to react with something in the serum. And that's why I said biological systems always surprise you, not only the computer system at BIPM. My intention when I submitted this abstract was to show you results. I unfortunately cannot show you just that we are working on it. And I still have some ideas how we can separate the ferritin here more successful. So we have already started to prepare immunoaffinity chromatography to actually capture our ferritin in here. But at the moment, we are unfortunately unable really to use isotope dilution and quantify ferritin in serum. So the outlook is we want to, or our colleagues in Vienna want to characterize the spike material more closely using reversed IDMS, and then use it also to characterize the calibration material of ferritin. We definitely have to improve the separation of the ferritin from other serum proteins. And here I also have some support from our organic colleagues who want to help us to identify the interfering proteins first so that we can find a more targeted method to remove them. And the final goal actually is to quantify ferritin in serum, in cerebrospinal fluid, and also in brain homogenate we get from our partners from mouse models for Alzheimer's disease. To be sure that we in the end really measure what we think we measure, we want to apply as many methods as possible. So our colleagues will start quite soon to develop an alternative measurement procedure using specific peptides. You can see the peptides here for the heavy chain and for the light chain. So we chose peptides that have hardly any PTMs or post-translation modifications that can clearly be achieved by tryptic digestion, so you don't have any miscleavages here, and so you can use it quite well for quantification. So after all this trouble, I'm already at the end of my presentation. I want to thank you very much for your attention and EuroMed for financing this work.